Welcome to Third Angle, where digital tech is transforming space travel. I'm your host, Paul Hames from industrial software company PTC. In this podcast, we share the moments where digital transforms physical and meet the brilliant minds behind some of the most innovative products around the world. In this episode, we head to Florida, home to NASA's Kennedy Space Center.
In 800 feet, turn right onto NASA Causeway.
It's been more than 50 years since NASA's Apollo mission put the first man on the moon. It was the late 60s, back in the days of pen and paper calculations and analog engineering protocols. But today, the NASA engineers at Kennedy Space Center are preparing for Artemis II, sending a crew of 4 around the moon and in later missions landing the first humans there since the Apollo landings in the early 70s. And NASA's digital transformation is going to help them do it.
I grew up in a small community in northern Manitoba, so never in my wildest dreams did I think I'd be working for NASA one day. To be able to contribute to space exploration, to be one of the people on the team that sends astronauts into space, trying to figure out how do we live in space? How do we live on another surface? That's just a dream.
I'm Trish Nicoli. I'm the digital engineering deputy program manager. I also am the technical tools and processes branch chief here at Kennedy Space Center. I manage the different engineering tools and engineering processes as we design and develop the rockets. When I first came to NASA, it was very paper-based. Everything was paper. You'd check out a physical book that had the procedure. You'd type up the work procedures. We'd print them out. We'd take it to the operation, and we'd go through the steps. You needed to carry around a physical stamp and ink pad, and you'd physically stamp saying, yes, we completed this job. This space here at Kennedy Space Center, it's several acres, and so if I was here doing a job in the vehicle assembly building, I might have to drive 20 minutes to go get my manager's signature. And so 20 minutes one way, 20 minutes back, that's an hour. And now you don't need to do that. It's all done on computers. If there's issues or problems, I don't have to physically go find somebody. I can send it to them electronically. You don't have to go to everyone's desk. So it's a huge time saver. As these different work control steps are bought off, you can see exactly what happened, exactly when it happened. So it helps buy down the risk to the schedule, the risk of technical errors. All of that can be easily traced through the work control systems, through the CAD systems, through the analysis systems. And so we have a very good picture of the system and its configuration.
So over time, the approach to engineering has changed. Obviously in the Apollo program, we were literally using pen on paper, or pencil on paper as it would, to do the drawings. It was very hard to be precise with the design, the weight, and what have you, make sure everything fit. There was a lot of launch attempts and failures before the Saturn V was finalized for flight. So they had the luxury of being able to build, test, fly incrementally. Well, in today's environment, we don't have that luxury. We have to get it right the first time. Terry Hill, I am the digital engineering program manager for NASA. It's been a gradient of change with time, going from the drawings to more of the CAD model, which then produced the drawings, and then later to using CAD computer-aided design 3D models. Where we are today is we were able to create a full interactive, integrated 3D model of the launch pad, the mobile launch platform, the rocket, and everything associated with that. Using the modern engineering design tools and the CAD tools, we're able to do all those parameter checks to make sure everything fits down, within the fraction of an inch in ways that we would not have ever been able to do back in the Apollo program.
The Artemis II SLS, or Space Launch System, is assembled in a massive building called the VAB, or Vehicle Assembly Building. It's actually the largest building by volume in the world. On the side of the building, there's an American flag, so large you could drive a bus down one of the stripes. Inside, a 16th floor platform allows you to look down, if you're brave enough, onto where the assembly operation takes place.
Wow.
been skydiving, but this still makes me nervous.
Be careful not to drop your phone. I'm not really into heights. Hi, I'm Christal Jolly. I'm the NASA Core Stage Operations Manager here at Kennedy Space Center. I work in Exploration Ground Systems, and my job is to perform all the integration of all the hardware and all the technical issues that we may have and work those out on the floor. When I was 10, I watched this movie called Space Camp, which if you haven't seen it, you should watch it. And I came home from the slumber party and I told my parents, I'm gonna work for NASA someday. I'm gonna launch people to space. It's a really rewarding job. I mean, I have fun. I don't even feel like it's a job, to be honest with you. I come in, I'm here 6 days a week, but it doesn't bother me because I love what I do. It's just so cool. I mean, I get to build rockets. They're gonna take people to the moon.
16 floors down, the floor of the VAB is a huge space, where each part of the flight hardware comes in, and then begins the critical assembly process. There's the spacecraft itself, the Orion capsule, which houses the astronauts, the core stage, which contains the fuel and all the essential technology, and the SRBs, or solid rocket boosters. And all of this is then stacked on top of the mobile launcher, which will be carried out to the launch pad a few miles away atop a mammoth vehicle called the crawler. And when it comes to rocket science, well, it's rocket science, so precision is key.
So currently we're standing in the low bay of the Vehicle Assembly Building. The VAB was built for the Apollo program, building the Saturn V rockets. So you can see where the red platforms are right there? That's actually old Saturn V Apollo hardware. So when our flight hardware comes in, it comes in through the transfer aisle in pieces. The core stage is here right now in the transfer aisle. And what we do is we actually lift it kind of like we're going up to the roof, and there's an opening at the very top. I think the 16th floor that we would be going up and over. And so we move that flight hardware over through the opening at the very top up there. These platforms that you're seeing, they don't move out of the way. They stay, they're fixed, and then we bring it all the way down, then we'll stack it onto the mobile launcher.
And is there a sense of nerves?
Very much, yes. For this, it's a little bit different than when we did the shuttle program. So the orbiter itself is $2 billion. So when we were hanging from that sling, it's a $2 billion piece of flight hardware. But we had done it a number of times. For this is only the second time we've ever done it, and I have an entire new team that's doing it. So the first time that they do it is only the second time it's ever been done. So what we're looking at right now is Core Stage 2, which is for the Artemis program. To give you a sense of the scale of how large Core Stage is, it's 212 feet and it's 215,000 pounds approximately. The Core Stage is the tank that has all of our fuel in it. So it's got our oxygen, it has our hydrogen, but it also has our flight instrumentation. It's got the cryos, it has the flight termination system. It's like the heartbeat of the rocket. So just a few weeks ago, we actually did the weight and CG of Core Stage. And how we do that is we hook up the cranes to the forward and the aft, and we actually use something called the SPMT, which are these little remote controlled cars essentially, and they go up underneath the core stage and they help lift the core stage.
So then we take all that information that Christal's team does in terms of figuring out the weight and CG and then feed that back to some of the modern digital engineering tools which then perform the analyses. For example, the guidance, navigation, control theory, because CG and weight obviously affect the performance of the vehicle and the flight profile and what have you. So effectively by having some of these core elements which may have not been either possible to collect before during the Apollo program, or at least not to the level of resolution that we have, and of course having the analysis and the analytical capabilities to look forward in time using this core measured information. So once again, we're able to optimize the performance and reduce the risk that we just would not have known on launch day before.
Back in the Apollo days, NASA used to keep earlier iterations of hardware sitting around. Twins, if you will. Engineers building a vehicle for an upcoming mission could reference the old hardware, experiment, model, test. But it can be expensive and time-consuming to operate that way.
We usually call those physical assets either hangar queens or iron birds. And effectively, they were used to do exactly, the anomaly resolution. So like on Apollo 13, we had all this hardware that was sitting either in a payload bay or somewhere specifically for the purpose of issue resolution. So, but now with digital engineering, a lot of that can be done virtually. So if you have a digital twin that is the virtual representation of something that exists in the physical world, then not only can you do the anomaly type of investigation, but you can also, run these models faster than real time to look into the future. That is kind of the different way we're doing business today to help reduce the risk without having to increase the cost of building a separate piece of hardware that's, volumetrically and has the same mass just to see if it fits. Right now, using digital engineering, we can use the CAD models and the 3D environments and the VR environments to really look and see what is possible and if there's any problems ahead of time. Again, to help reduce the risk and the cost and schedule. So this is really allowing us to be more nimble, flexible, and more cost effective.
So we spend a lot of time in our Design Viz lab where it has all of our drawings, our CAD models, and we work with the team and make sure that, hey, this is where it says it needs to be, and we work it out in the computer systems, and hopefully it's going to work like it's supposed to now. What I was looking at the other day, it was removing basically kind of like a coupler, this specific piece of flight hardware inside the core stage that we have not accessed before. So we went over there and said, okay, can we get to this? What if we squat here? What if we put our arm here? So that if we're in the middle of a job and now we don't know if we can access it, we can stop the job, come into our Design Viz lab here in the VAB, test it out to see, yep, we can get access, nope, this is a problem, and that we can work it real time. And it is accurate down to the bolt.
So currently we're standing outside the VAB beside the crawler. It's a very large structure, and there are 4 large tracks on each side of the vehicle. The mobile launch platform sits on top of it, as well as the SLS, and it drives the whole stack out to the pad. So this vehicle can carry 18 million pounds. It goes 1 mile per hour when it's fully loaded with the vehicle and the mobile launcher platform. The journey out to the pad takes between 7 and 8 hours.
You can see how the sheer weight of this vehicle and the stacked assembly have taken rocks that are about the size of your fist and basically crushed them into a fine, compact powder layer. It's really humbling to witness the size, the scale of what this vehicle can do. Being able to take the entire launch system onto a completely clean launch pad was unheard of during the Apollo program, but that's some of the capabilities that we're able to do with this modern approach.
You do have people that walk beside it during any of the major transport or major moves, just because it's always a historic occasion. Christal, you've walked beside this as it's been transported across, right?
Because it's a very long walk.
Yes. So nobody wants to do it that long.
Wants to do it.
Usually you see people kind of walk out and then they're like, all right, that's far enough.
Yeah, they're like, oh, this is good. I got my picture and now I don't want to walk anymore.
Yeah.
It's launch day, and after the massive crawler carries the spacecraft, complete with its solid rocket fuel boosters, out to the launch pad, the countdown is near. And then begins the delicate operation of fueling the rocket with its liquid fuel.
So the Artemis mission and the vehicles associated with it, we've got a mixture of liquid rocket fuel and solid rockets. So the 2 boosters that strap on to either side of the core structure of the Artemis rocket, those 2 on the side are solid rockets, which means the fuel itself is a solid fuel, which is how it allows us to stack those individual segments and build up the solid rockets here in the VAB. Once those are lit, there's no putting them out. You just got to let them burn until they're done, which makes them, very powerful, but also makes them very dangerous.
So if you look to either side of the pad, on the right side there is 2 liquid hydrogen tanks, and then on the opposite side there's a liquid oxygen tank. During tanking, which is fueling the rocket, they actually get fueled into the core stage and the ICPS. One of the major changes that that happened between shuttle and Artemis is the fact that this vehicle is so much larger, so we needed more hydrogen. And so a second tank was built, and using existing piping that was already in the pad to fuel the new rocket. And so through using simulation and digital engineering, we were able to show that the flows and the ability to do parallel tanking of the ICPS and the core stage, we were able to satisfy that that actually worked before we actually tried it for real.
When we start launch ops and we're actually going to launch, the 4 shuttle main engines that are heritage engines will ignite, and then the SRBs ignite. And once those SRBs ignite, you're going to space. Like, there's no turning those off, you're going.
So a big part of human spaceflight is, making sure the humans are safe, because, we've certainly had our accidents in the past that we've learned from. So with the modern approaches to digital engineering, that allows us to be able to run more what-if scenarios with higher resolution by reducing the risk and increasing the safety margin. The accidents, they hit very personally because quite often you have worked side by side with the people that have lost their lives or gotten injured. So it's a very personal thing for a lot of us when that happens. We do take all of what we do very, very seriously because we know the people that are being put out there, right? It's really a lot of responsibility, and I take it very seriously. But I believe in the mission of NASA and believe that it's critically important that we continue to evolve in every domain.
When I first started out here, we did not have a lot of women doing, the systems engineering of the different teams. Back when I was in shuttle, a lot of the jobs I had, I was the first and or only woman to ever have that job. And so now we have, our NASA test director's office have multiple women engineers in it. We've got to get out there and try to encourage the young folks to come into engineering and STEM fields, including girls are not exposed to that kind of thing, at home or in their schools. And sometimes we'll do special tours out here, and then they get to see it for real. And those ones, I feel like we are reaching the ones that might be on the fence. The ones are like, I want to do engineering, but I think it might be too hard, or I want to do engineering, but I'm not 100% sure because it's a lot of math or it's a lot of science. But then when they get to see the flight hardware and this is what they're going to be doing, that kind of sends them over the edge, like, this is actually what I want to do.
When I started with NASA in 2001, a lot of times I would be the only female in the room, and sometimes it was scary to think that I could speak up. As I got more experience and exposure, I was able to speak up and I was listened to, and a lot of the managers, a lot of the people around me have always encouraged me to have my voice. And it's also nice, as I sit in a lot of these different meetings, I'm not the only woman in the room anymore.
NASA is continuing to evolve, and it hopes its digital transformation will help make spaceflight exploration even more efficient than it is now. A big part of this development is partnering with experts outside of NASA. In years gone by, spaceflight was primarily led by NASA alone. But Terry says that's changing. NASA has a more open relationship with industrial partners, sharing missions, sharing data, all with the hope that the brightest minds across the world will facilitate the next technological leaps in space travel.
Truly, we are going back to the moon with an entire team of industry providing critical components, outside of the integration role that NASA used to play in the past. So it's a completely different playing field that I'm not sure they would have ever imagined, back in the 60s. It's critical that we all take this journey together, because without any one of us, we're not going to get there. And I think it's important to the space program. I think it's important to the United States, but not to sound too grandiose, I also think it's critically important for humanity. So I think overall, it's a weighty responsibility, but one I'm happy to be part of.
We spend years getting ready for the launch. And so when it rolls out, you're getting one step closer. Trish and I started on this program when it was in infancy. You know, it was nothing, it was just on paper. And to be able to watch it from paper, and it's an idea and a concept, to getting here and launching is really an amazing feeling. It feels like magic to me. You know, it's like science, but it's, you know, magical, and you're watching it, and it's just something to be proud of to be able to do this. For Artemis 1, and I'm sure Trish feels the same way, we had multiple scrubs before that because of leaks. And I remember when we got down, I was running the Launch Control Center at the time, and I was watching it with our landing director, actually. And we were at T-minus maybe 15 seconds, and we just looked at each other and we're like, oh my God, we're gonna do it. Like, this is it. We're actually going to launch today.
4-stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis 1.
When those rockets light, the air just vibrates. So you'd feel the sound just permeating through your body in waves and vibrations. And add to that the sight of the rockets going up, and it really adds to the, as Christal said, the magical nature of this. It's in addition to a sense of awe of seeing this thing come to completion.
And so it's a lot of hard work. It's a lot of long hours. And then just knowing something up there is in space that you worked on, that you helped build, and it's a legacy for the human race.
Started out here when I was 16 as a high school intern. This is all I've ever done, you know, is worked out here. And it's just knowing that the hardware that we put on the shuttle is now in space and it's being used, and it's like you're leaving like your little tab in history of all the things that you got to sport out here, and that's pretty amazing.
Special thanks to Trish Nicoli, Terry Hill, and Christal Jolly for taking us on an incredible tour of Kennedy Space Center.
All of us that had worked the shuttle program, we all signed our name on this wall. So that's why they have it kind of blocked off so nobody takes any of the signatures down. But you can go back and you can look and see some of the astronaut crews signed it. Oh, there I am. See, Christal Jolly, right there.
Please rate, review, and subscribe to our bi-weekly Third Angle episodes wherever you listen to your podcasts, and follow PTC on LinkedIn and X for future episodes. Companies that make products the world relies on rely on PTC. This is an 1860 production for PTC. The executive producer is Jackie Cook, sound design and editing for this episode by Sarah Joyner, location recording by Gareth Evans, and music by Rowan Bishop.